Alright, so this is a continuation of what we did last time. In the last time I introduced the definition of a derivative, and I talked a lot about the exponential function in this Taylor series. I'm realizing now that I kind of skipped a lot of things before I talked about that, but since you guys already took calculus, I think the last video was quite understandable in itself. So let me continue with talking a bit more about the Taylor series. Okay, so, well, what is a Taylor series? Well, the Taylor series actually came from something called the power series, and I'm not going to talk about the full derivation or the full proof of how Taylor series existed, as that is more suitable for an analysis or advanced calculus class, and this is not an advanced calculus course. So, if you want to know about the proof or the derivation, I will add it on my advanced topics for this course, and you can see it there. However, let's continue. Basically, the Taylor series came from something called the power series, and the power series is a continuation of a polynomial if you think about it. So here's the power series, right? The power series can be understood of some k equals 0 to infinity, right? Of a to the k, right? Suppose that there's some a to the k, z minus a to the k. And suppose, if I don't like the letter z here right now. X minus a to the k. The reason why I didn't write that because later on in complex analysis, z is used for complex numbers, and here we're talking about absolutely real numbers. And the idea of the derivation is if you take the derivative, if you take k's amount of derivative, k's derivative of this function, right? A sub k, right, is gonna be equals to f prime of k's derivative of a of k factorial. So what this becomes is it becomes a Taylor series. So this becomes, and if you take the case derivative of this, taking the case derivative, we get is that we can get the f of x, right, equals to sum of k equals to 0 to infinity of f to the k's derivative of a over k factorial times x minus a to the k's power. And this is what we know as something called as the Taylor series. So this is the Taylor series. Taylor series centered at x equals a. At x equals a. Okay. So what happens? So let's look at the Taylor series. Here, let's look at the Taylor series. Centered at the origin. Right? Let's look at the Taylor series centered at origin. And this is also not the Maclaurin series, but so if it's centered at the origin, so if it is centered at the origin, right? This means a is going to be equals to 0. Okay? A a is going to be equal to 0. And if a equals 0, what happens? Well, f of x, right, it's going to be sum of k equals to infinity, right, f to the case derivative of a of k factorial, this doesn't change, right, times x minus 0 to the k, right? And obviously here, this is the same thing as the sum of k equals to infinity of f to the case derivative of a over case factorial of x to the case power. And this is something known as the Maclaurin series. This is something called the Maclaurin series. And so here's a theorem that I'm gonna give without even really proving it. So Taylor's theorem, what does the Taylor theorem say? So here, Taylor theorem. Suppose f of a and b tend to the reals is a function in a and b, where a and b are real numbers, and here for additional information, b is going to be greater than a. No surprise there. Assume that the function f is case differentiable. On the interval a and b. On the open interval a and b, then and f prime, f double prime, and etc. are continuous or extended continuous on the closed interval a and b, such that there exists a c, in the open interval of a and b. And so, and then if we say that, then we can say that f of x is equals to the sum of k equals to 0 to infinity, right, of f to the case derivative of a over case factorial times x minus a to the case power. Okay? And we're not going to prove this because, I told you the reason why. But instead, we're going to go back to our previous lecture and see how this works. So, example. Okay, if you want to see the proof of this, you can see an extended version or the advanced version of this, and I'll give you the proof, but the proof of this is more suitable for an advanced calculus class, not a beginning calculus or engineering mathematics class. Anyways, so in the previous lecture, I said e to the x, right, is equals to sum of k equals to 0 to infinity, right, of x to the k over k factorial. And I'm sure I left many of you guys wondering how the hell I got this. So because there's two things we realize here. The first thing is that this is centered at 0. Or no. At a equals 0. Second thing is, how did you get the question is, how did we get this? Right? Is this even true? And those are valid questions. So let's try. So the first thing you realize from Taylor series is you have to take the case derivative of this. So we know a equals 0. So obviously we're just dealing with a Maclaurin series here, which is centered at 0. So the first thing we do is we evaluate everything at 0. So here it is. What is f of 0? Right? Well, so let's be more organized. If f of x is equals e to the x, right? Then what? F of 0 is what? E to the 0, and this is equals to 1, right? Consider this. Let's say f prime of x, right? The derivative of f of x is e to the x, right? Doesn't change. F of 0. F prime of 0 is just 1. Because same thing, right? And in fact, all the way to, f to the n minus, we're using k, sorry. So f to the k minus 1's derivative of x is going to be e to the x. This means that f prime of k minus 1's derivative of x is going to be 1. But here's the thing. The derivative, right? So this section here speaks about, the f to the case derivative of a, right? But it's f to the case derivative of a over k factorial times x to the k. So e to the x, right? E to the x in series notation is pretty much equals to the same thing as this. So here we plug in 1. We start from 0, so it's 1, right? 1 over 0 factorial, right? X to the 0, right? Plus, this is first derivative, right? So 1 over 1 factorial times x to the first power, right? Plus, the second derivative is going to be 1, right? 1 over, but k equals 2 now. 2 factorial x squared, right? And if you have 3/3 power, it's just going to be 1 over 3 factorial x cubed, and so on. Right? It's going to be so on, right? It's pretty obvious. So, if you expand this, if you see e to the x, right? 0 factorial is 1, by the way. Is 1. X to the first power is just x, so we have x plus 1 over 2 factorial x squared, and plus 1 over 3 factorial x cubed, and so on, right? So this is how we got e to the x to the k factorial, and that's why we can prove using the quotient difference. In the last video, we said that the derivative, so the limit, that's why we can prove that the limit of some h tends to 0 of e to the x plus h minus e to the x over h is really e to the x, using this factor right over here. Without it, we cannot really prove this at all. But there's also ways to prove this. But this is one clever trick. So let's do another one of these examples. And let's do more, and in this lecture I'm going to do more quotient difference examples as well. Let's do another one. Suppose we want to prove another function. Before we find the Taylor series of this, let's try to prove what is the derivative of y equals to sine x. Sine x, using quotient difference. And then after we get the proof of that, let's try to solve for the Taylor series of the responding things. Okay, so, well, if you use the quotient difference here, f of x plus h, right, is sine of x plus h. And this, I'm going to write it in red actually, is not equals to sine x plus sine h. Okay, this is one of the most rookie mistakes that anyone makes, but it's not. It's absolutely false, and this doesn't make sense. So sine of x plus h by addition theorem in trig is sine x cos h sine x cos h cos x sine h. Okay, but this is by addition term. Okay, so let's see, and then we have that f of x if it goes to sine x, right? So let's take so we're going to use this identity right over here. We're going to use this identity right over here to find the quotient difference. So, see, the limit as h tends to 0 of sine of x plus h minus sine x over h. Okay? And this, by addition theorem, we can prove that as h tends to 0, right, of sine x cos h plus cos x sine h minus sine x over h. Okay, so the trick is in here, we move this thing here to right over here. Okay, so what happens is limit as h tends to 0, right, sine x cos h minus this is bad, sine x cosine of h minus sine x, right, plus cos x sine h all over h. Right, and here we can see, ignore this term here. So here we can see the sine x and sine x, right? So we can factor that out. So we have is the limit as h tends to 0, right? Sine x times the cosine of h minus 1 all over h. Right, this is the first limit, plus the limit as h tends to 0 of what? Of cosine x sine h over h. Now, rewriting this, because h tends to 0, right? Not x tends to 0. The sine x and cosine x comes out. So this is what happens. Sine x, right? Times the limit as h tends to 0 of cos h minus 1 over h. And you'll realize that if you take the limit of this as 1 minus 1, 0, 0, and even if you do any kind of trick to this, you're just gonna get 0. So this becomes 0. Okay? This just becomes 0. Alright, so that's useless. Plus the limit of plus cosine x, because h tends to 0, the limit as h tends to 0 of sine h over h is, and I'll soon prove this, but this is a special limit. You have to recall that from Calc 1 that the limit as h tends to 0 of sine h over h is just 1, in honesty. So this is going to be cosine x. Cosine of x. So we can prove that the derivative of sine x is cosine x. Now, if you do the same thing for cosine x, the derivative of cosine x equals to minus sine x, and I will leave this as an exercise. You can use the same technique, just that you have to find the addition theorem for cosine, not sine. Okay, so I'll leave this as a technique. So suppose we know these two things. Right, we know these two facts, okay? And I told you to find a Taylor series for sine x. Centered at 0, the origin for y equals sine x. How do we do it? That's a question, okay? So let's try this. I don't know if this is going to work out very well, but yeah, let's try this. Alright, so it's the same thing. It's centered at 0, so a equals 0, right? Because it's centered at 0, right? So f of x is what? Sine x, right? Right? So f of 0, right, is what? 0. I mean, sine of 0 is 0. Right? So here, f prime of x is cosine x, right? I mean, f prime of 0 is what? 1. And we can continue. F double prime of x is what? Negative sine x, right? So this means f double prime of 0 is what? 0. And let's see if we find the fourth derivative. F triple prime of x is equals to, so the derivative of negative sine x is, sine of x is cosine x, so it's negative cosine of x, right? And the f triple prime of 0 is just negative 1, right? And I'll stop in the fourth derivative, but I'll show you this one. F to the fourth derivative of x, right? And usually after the third derivative, you write the number. Cosine is negative sine, so it's positive sine x, right? That means f to the fourth derivative of 0 is equals to 0. Alright? So you clearly realize a pattern here. I mean, 0, 2, 4, 6, 8. even number of things is going to be just 0. But anyways, so let's try this. So sine of x really is equals to 0, nothing, 0, plus 1 over 1 factorial x, right? X minus plus 0 minus, let's make this clear. This is 0x squared, right? Minus, because it's minus 1 here, right? Minus 1 over 3 factorial x cubed plus 0 and so on. So really sine of x is equals to x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7. You can really prove this just by yourself. This is a no-brainer. You can do more expansion. You can find this out by yourself. I'll leave that as an exercise as well. And eventually, you get is sine x really is equals to the sum of k equals to 0 to infinity of minus 1 to the kth power x to the 2k plus 1 over 2k plus 1 factorial. Okay? Alright. Alright, so yeah. This is the thing. And if you find the derivative of, if you find the Taylor expansion for cosine of x, you're going to find that cosine x really equals to the sum of k equals to 0 to infinity of minus 1 to the k of x to the 2k over 2k factorial. And this tells you something special, actually. And the special thing that it tells you is that from this, so assume 2k plus 1, right? We have some n is equals to 2k plus 1, right? For every k part of integer. So k, this sign here means an integer, meaning minus 1, so the set of integers, if you recall, is equals to minus 1, 0, 1, 2, and so on, and so below, right? And so below. And so, for example, 1.5 is not an integer. Okay. Alright, so integer can be any negative or positive number that is like 1.00 or negative 5.00. Okay, so for any case integer, right, plug in k equals 1. Alright, 2, 1 plus 1 is 3. It's odd. This is an odd number, right? Right, so plug in 2. K equals 2. 2 plus 1 is 5. Odd. And eventually you'll find that for all integers, so for all, this here means all integers, for all k belonging to an integer, okay, 2k plus 1 is odd. And similarly, this is for all. This is for all. And similar for all. Similarly for all k belonging to an integer, 2k is even. Okay, and the reason why this is important is that from this series itself, you can tell, because of these terms here, right? From these terms here, we can tell the first we can tell that sine of x is an odd function. So, by definition, an odd function is it is an odd function when f of minus x, right, is equals to negative f of x. Okay? But because of this, we can say this is an odd function. And b, cosine of x, is an even function. So f of minus x is equals to positive f of x. And this is the definition of an even function. So I'll stop here for now, and we'll talk a bit more about the Taylor series and things like that next time, and do an example of an integral problem that I really wanted to do with you guys, actually. And that's it for today. I hope you the best luck, and I hope you enjoyed. Thank you. Bye.